Hello everyone and welcome to EdTech channel. Today we are solving one LeetCode easy task, Fibonacci numbers. First we will see some intuitive solution using the recursion, and then we will move on to the more efficient approach using dynamic programming. Fibonacci sequence is sequence starting from numbers 0 and 1, and each other number is the sum of the latest two numbers. So the second one is 0 plus 1, which is 1, then 1 plus 1, which is 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, 5 plus 8 is 13, then 1, 4, and so on. Our task is for given integer number n to calculate f of n. So let's write the pseudocode first. If n is 0, that is the special case when we need to return 0. If n is 1, we need to return 1. Otherwise, we need to call the same function for n minus 2 plus the same function of n minus 1. And let's transform this pseudocode to C#. Now we're almost there. Okay, and let us try to run and submit our code. Okay, we are good. Our solution is accepted, but our runtime is not so good. Only beats 10% in the LeetCode for this solution. So now let us see how we can improve this and where is exactly the problem. So let's investigate why our previous solution was so slow. So imagine we want to find f of 10. And we are starting from number 10. We are calling function f for 9 and f for 8. To calculate f of 9, we are calling f of 8 and f of 7. To calculate f of 8, again, to calculate f of 8, we are calling f of 7, f of 6. Notice that, for example, f of 6, we are calling here, 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 and we would call it here again, and so on. So, for such a small input, n is equal 10, we are calling f of 6 1, 2, 3, 4, 5 times. So, we have a lot of repetitions. So there is no need to call the same function for the same number so many times. We can keep in some Fibonacci array, we can keep previously calculated results and use them instead of calling the function and do the whole calculation each time. Fibonacci array of 0 is 0. Fibonacci array of 1 is 1. Fibonacci array of 2 is 0 plus 1, which is 1. Fibonacci array of 3 is first and second, which is 2. Of 4 is the sum of previous two, which is 1 and 2, 3. Fifth element is 2 plus 3, which is 5. Sixth element is 3 plus 5, which is 8, and so on. So we can set our array of 0 is 0, our array of 1 is 1, and any other element is sum of previous two elements, f of n minus 2 plus f of n minus 1. So instead of calculating f of, for example, 6 each time and do the whole calculation, we will only access it in memory, which is a constant operation. Let's see how we can implement such solution in code. We want to keep these two edge cases, but here, instead of recursive calls, we would create additional array in memory. It will have n plus 1 elements because it starts from 0, and there is in total n plus 1 elements. First one we can initialize to 0, second one to 1, and then each other starting from index 2 up to n. We want to initialize using previously calculated values. F of I is f of I minus 2 plus f of I minus 1 instead of these recursive calls each time. Then, at the end, we just want to return f of n. Let's now try to run and submit our code. Okay, good. So it's accepted, and our runtime is way better now. Now, let us discuss the time and space complexity for both solutions. So, the first solution was if n is 0, return 0. If n is 1, return 1. Otherwise, return f of n minus 2 plus f of n minus 1. The second solution, this part is the same and it's constant. And then we have array of n plus 1 elements. We had a for loop, and we calculated f of I. In this case, f is function, and in this case, f is array. So, with the recursive approach, first one, we had the following logic. As we displayed, we have 10, 9, 8. Then for 9, we are calling something. Then for each of these nodes, we are calling something. So in the first step, we have 2 calls. In the second step, we have 4 calls. In the third step, we have 1, 2, 3, 4, 5, 6, 7, 8 calls. And in each step, we have 2 times more steps. So for n is 1, we have 2. For n is 2, we have 4 steps. For n is 3, we have 8 steps. So the time complexity of this solution is exponential. The space complexity for this solution, because it's about recursion, it's the depth of recursive tree. So when we have 10, we will call for 9 and 8, 9 we will call for 8, and 7, and so on, until we come to the 1 and 0 sometimes, and the length of this tree will be n. We are going from 10 up to 1. So the space complexity is linear, even though we don't have any explicit occupation in memory. In this case, we have explicit occupation of memory. We have n plus 1 elements, which is big O of n space complexity as well. And here we are iterating from 2 up to n, and we have some constant operations. This operation is constant as well because it's about the array. So we have only for loop of n steps. So the space complexity is linear here as well. So we have the same space complexity in both cases. It's linear, but the time complexity is in the first case exponential, and in the second case it's just linear. The first approach is using a recursion. Second approach is iterative. We are using for loop, and it's called dynamic programming because we are saving in the array previously calculated values, and we are using them, accessing in constant time. That's it for today's video, Fibonacci number. I hope this video have helped you solve this problem and also to understand deeper the time and space complexity when we are dealing with the recursion, and how dynamic programming can help us to solve the problem more efficiently. Keep practicing and see you with the future videos.